In this work, we investigate how we can use a phone photographer's natural handshake to help reconstruct high-quality depth. Direct time-of-flight devices like LiDAR measure depth by the time it takes light to travel to and return from an object. Thanks to advances in sensor technology, structured light LiDAR devices have found their way into the modern smartphone. And with its help, these phones produce excellent indoor pose tracking results and visually consistent depth estimates. That means, as an imaging platform, our smartphone now offers us access to 60 FPS image, pose, and depth streams. Unfortunately, the mobile LiDAR has poor spatial resolution, and the curves over a decorative gourd are completely lost in the depth reconstruction. To recover these surface details, we bring in a new dimension: time. Instead of capturing a single frame, we design an app that captures a bundle of synchronized pose, depth, and image data. For even as a user tries to steady the phone's camera on a target, their small unconscious muscle movements cause the view to continuously shift. Averaging hundreds of handshakes for 2-second snapshots, we see that this movement is highly random and on the scale of only a few millimeters. The shift between each frame is a little over 1/10 of a millimeter, the length of the entire path is about a centimeter, and the maximum effective baseline we see is on the scale of 6 millimeters. Visualizing this motion in an anaglyph, we see that this results in only tens of pixels in disparity for close-range objects. Nonetheless, from a full bundle of these micro-baseline measurements, we can extract high-quality depth. We select one frame as a reference view, and can stochastically sample other query frames from the bundle to search for a refined depth representation that makes all these views consistent. That is, we use this depth to project a point from the reference frame into the scene, sample the corresponding pixel color in image space, and when we see the same point in a query frame, we enforce that it also has to see the same color when projected through the depth and image space. There are many choices for what this depth representation could be. For example, it could be a point cloud, but a 2-second bundle recording would result in hundreds of millions of redundant points. It could be a large depth map, but then we'd have to sample and interpolate over non-integer coordinates during reprojection. So we opt for an implicit depth representation, which lets us directly optimize over continuous spatial coordinates. Putting this all together, we arrive at our handheld depth refinement pipeline. We take a point on the query depth map, project it to the world coordinate frame, and sample the corresponding space on the reference image. For training stability, we sample a pixel neighborhood to form an RGB vector, which we pass into our implicit depth network, along with a positional encoding of the original query depth point. Rather than directly output depth, our network outputs depth correction term, hence depth refinement. We use this refined depth value to deproject the point into our query image frame, sample a new RGB vector, and calculate a photometric loss term to backpropagate through the network. To help better control for textureless regions in the image, we add an explicit confidence weight to this depth correction with additional details in the main text. For repetitive textured scenes with micro-baseline motion, prior work fails to recover meaningful object details or struggles to reconstruct background content in low-texture areas. The proposed method does both, recovering the surface structure of the gourd's curves and the hands of the thinker statue while gracefully falling back to the LiDAR depth in textureless regions. All this from a single button press and a single snapshot, with no additional hardware or artificial hand motion. Even for complex backgrounds where the phone depth struggles to determine what's an object and what's part of the carpet, our method produces robust, geometrically consistent results, particularly along the spires of the fish tank castle and the arms and ears of Ganesha. You can find the full work along with open source code and models online on our project website, light.princeton.edu/HNDR.